In problem number 2, we're also doing optimization in kind of a different capacity this time. We have the function square root of x minus 1, and we want to know which point on that graph is the closest to the point 11 halves comma 0. So let me just graph this. It's not necessary to graph this for this problem, but I'll just help you see what we're doing. Square root of x minus 1 is the parent function of f of x equals square root of x shifted to the right by 1. So this starts here at the point 1, 0, and goes over to the right like that as a square root graph. And we have the point 11 halves 0, which is 5.5, which is right here. And it's the y-coordinate is 0, so it's on the x-axis. And we're saying which point on this graph is closest to the point here. So it might not be obvious from the graph because a lot of these points are probably pretty close, similar in their distance, if it's all the way across or up this way or whatever. So we're trying to find which point on this graph. So let's say the point that is the closest, we don't know what it is, we'll call it x comma y because we don't know its coordinates. So now what we need to come up with is, what is the function that we're minimizing or maximizing? Well, if we want these 2 points to be the closest possible, 11 halves, 0, and xy, we want these to be as close as possible. That means we want their distance to be minimized. So we need a distance formula, and we need to minimize it. So there's one little trick that we can use here. Recall the distance formula is the following. So you have square root of the difference in x's squared plus the difference in y's squared, which if you think about it is really just like the Pythagorean theorem. Since we know distance is a positive quantity, minimizing the distance is the same thing as minimizing distance squared. Since they're always positive, if you want d to be as small as possible, that still means that you want d squared to be as small as possible. So the reason that I'm going to do that is because that just gets rid of the radical over here. And now when we plug in these points that we know, if we take this derivative and set it equal to 0, the derivative here is much easier because we don't have a radical over everything. So that's why I'm going to do that. So now we just need to plug in what we have. Well, our points were 11 halves 0 and xy. So we'll plug those into here. So the x2, it doesn't matter which one you call point 1 and point 2. I'll just call this xy point 2. So the x-coordinate of it is x, and the x-coordinate of the first point is 11 halves. So we have x minus 11 halves squared, and now we do the difference of the y's. Now remember, we're going to be taking the derivative of this and setting it equal to 0, and like in any optimization problem, you want your function to be in one variable. So we don't really want to put a y here. We don't have to because we know the function is root x minus 1. So x comma y is really just x root x minus 1. So that is our y. And I don't need to write anything else in there because the other y coordinate is 0, so it's minus 0. Let me square that. Okay, so this is our distance, and actually I can rewrite this slightly more simply. This is a square root by itself that's squared, so we just take that away. Get plus x minus 1. So d squared is equal to this, and if we minimize d squared, we get our answer. So we want to take the derivative of this and set it equal to 0. The reason that I'm not expanding this, because we're taking the derivative of it anyway, and this inner part has a derivative of 1, because it's just x minus a number, so we really don't even have to use chain rule. So there's no point in expanding all of that. We'll just take the derivative now. And we want the derivative to equal 0. So the derivative of this term is just using power rule. You bring the 2 down. You leave the inside the same, lower the power to 1. We don't have to multiply by anything because the derivative of this is just 1. Over here we get plus 1. Derivative of x is 1. That part goes away. So we want this to equal 0. This is really easy to do now. Just distribute the 2, and then we'll solve it. So if we distribute the 2 here, we get 2x minus 11 plus 1. Well, 2x minus 11 plus 1 is 2x minus 10. And if you add over 10 and divide by 2, you get that x equals 5. So the x-coordinate of our point up here must be 5. So to figure out the full point, we just need the y, which would mean we just plug it back into our function. So f of 5, square root of 5 minus 1, that's 4. Square root of that is 2. So our point is 5, 2. Because our x-coordinate is 5, we plug it back into the function and get 2. So this point right here excuse me, is 5, 2, and that is the closest point to 11 half 0 on that graph.
The Teaching Center, UF's Learning Resource Center.